Hello everyone, welcome back to Computer Vision 1. And then finally we are getting to our fifth week, and then it's glad that everyone made it to the fifth week, and then that is more than half of the course now. We have 3 weeks to go, and also that I totally understand this year will be especially difficult, especially I just see and noticed that one of our students, and then her roommates got infected. So please be very careful and also be very responsible to your other classmates. Just in case there's anything, please let us know, and also let the university administrators know as soon as possible. But other than that, I wish good luck for everyone. Here's one more thing that our senior TA, Peter, he is happy to give one lecture on object detection, so that next time that he will do a guest lecture for us, but technically he is not a guest, and I hope you guys will enjoy it. From this week, we finally go to the high-level vision. We start with object recognition, backup words, then we will do object detection in the Thursday lecture. Plus, we will start introducing convolutional neural networks. Um, so finally, you guys will need to use quite a few technologies from um, machine learning. I know that there are those things that a lot of them is quite difficult because there's a lot of mathematics in it. But well, hope you guys have already mastered it, and a lot of this concept will be needed from now on. And good luck. So again, we are showing this photo quite a few times. That we finally go to the last step of the computer vision problem. So we really want to know that not only that when we show the image, we talk about the pixels, we talk about the color, then we talk about a little bit about where's the edge, where's the interesting points. Now we finally go to discuss the problem. Can we tell like this is a human? Can we tell that who is him? Is this a particular human? And also, can we tell that what this person, assuming that we already know this is person, what this person is posing? Or we try to tell more, like, is this person doing anything? And again, we're showing this picture pretty much every time that if you have to structure this kind of technology in computer vision, we usually structure it as a high-level vision. That means visual detection, recognition, understanding. We will also quickly introduce some other concepts in later, that including semantic labeling or activity detection, event detection, etc., etc. Um, well, it doesn't mean that the high-level vision is kind of like better than low-level vision, but the problem why it's called high-level, as you can see, these things is more related to the concept of an image rather than a physical word. But however, also that we found that if you really want to analyze those things, you have a very heavy dependence on the other level of vision technologies. For example, the low level one, the image capturing. Because if you cannot even capture an image, or you capture a really noisy image or damaged image, then that there is too much to talk about how to analyze those image. So this kind of thing, like this high-level vision, is usually be considered quite dependent on the mid-level and low-level vision. Here's the outline of today's class. So we will mainly focusing on object classification, and then we will talk about quite a few things, starting with the feature presentation, backup words, and then we start talking about feature space, decision boundary, and then we start talking about precision and recall, which is the way to evaluate our object classification methods. And after that, we will talk about some other tasks, image retrieval and image segmentation. I showed this photo in a very early course lecture. So why we don't just compare visual system to a computer vision system? Because now we have neural networks. I just confirmed that you guys have studying with the Boltzmann machine. Well, first things first, that of course, the number of neurons is still quite different. And the second, actually, the neural network nowadays is working quite different as a computer. Although we start having these convolutional neural networks, but the mechanics of it is quite different from the human neurons. And especially if you guys have any background in electrical engineering or circuit and system, you guys probably will have an understanding that this neural networks was actually coming from a lot of those things that was physically from transistors and diodes, which is rather not really that directly inspired the human neurons. And also, I think in the first lecture, I told everyone this story. So nowadays, if we show all these cool videos, that things really started working. But back into a century ago, that was in 1966. So these things like even the professors believe that things could be simple, but it never is. Nowadays, what is actually kind of a little bit over optimistic. There's something like autonomous driving. So we know that Tesla has released their autonomous driving cars quite early. And also we know that the Mobileye has quite a few technologies which looks really cool. But we know that it's been like since Tesla releasing their first mobile autonomous car, it has been more than 5 years already. Then we know that there's no obvious breakthrough yet. Like there's no like a serious like a non-driver car on the market or on the road yet. So we know that there's a lot of things to do yet these things look so cool, but still quite far away from a real human vision system. So that's why the computer vision research is still continuing and it's really growing currently. But we are still quite early from those things. We still start with a very, very fundamental and preliminary introduction of the general ideas. But let's start. So why image is important? Because it really tells you what is what. Like title says, an image is worth than 1,000 words. So for example, if you really want to describe this image, then you really need to write a really long and detailed paragraph about there are people there, it is a square, it's a cityscape, there's outdoor, there's building, there are trees, and the trees was in a far way, and close to the point that we are observing, there are a lot of people, and most of them are tourists, and then some of them are local people. They're young people, they're old one, etc., etc. So you see that there are all those things that is restored in a pixel that actually is so informative to our human vision system. But if you really want to, convert and extract everything from it, you find it's actually so rich of information. Usually I play a real-time demo for this one. So this is very important, a very, very important database if you're trying to do object classification or object recognition. Because in machine learning, we know that regardless if you're doing mm, supervised learning, unsupervised learning, first things first, you need data. There's nothing like no data learning. So where do you get data? And you get visual data to learn. So one of the most important databases is ImageNet. So for example, there's a random image here that which are insects, which are showing here. So all you can do is that you can search one of them, and you got things from the database. The good thing for ImageNet is because it's open, and then you can just call the images, which is currently this is something out of date. Currently, I think there's more than 20 million images or around that number. Then you can use such a huge amount of data for your machine learning or algorithm. But of course, there will be huge companies like Google and Microsoft. They also do their image search. They also have a very huge database, but those are not open, so you can't really get it. But for ImageNet, one of the good things is everything is open to public, and you can download it for your research or project. Usually, if it's a real physical class, like I said, I was trying to ask you guys to go through surf a little bit of the ImageNet. But this is a pre-recorded lecture, and then I strongly encourage, if you guys have time, definitely go to this website and search it a little bit yourself. We need to actually have a few terminologies in which we usually use in computer vision. The first one is object classification. It means that they're usually in an image, there will be only one object, or that is actually one important object. Then we need to know that what this object is about. And then we also have a visual image retrieval, which is quite similar. The idea is quite similar, like you do the Google image search, so that you usually want to give a query that you query key words. Then you want to get all the images about that follows these keywords from a database or library. And then another thing that is slightly little different is the visual image retrieval, which means that the query does not necessarily to be a word. It can be another image. It happens, for example, if you want to do some online shopping. If you happen to find one thing that you really want to buy, then you don't know what this thing is, so you can't really, shop or search it using, the name of the thing you want to buy. Then one good thing you can do nowadays is that you take an image of those things you just found, then you let the visual image retrieval do the rest. They will find the most matched object in the system. Object detection is about like in an image where there's any object that exists. For example, pedestrian detection is quite important in autonomous driving. So as vehicle detection. The first things first, if you want to autonomous driving, that once you get your camera from and the image, you definitely want to know whether there's cars, there's pedestrians in the image and where they are. And image segmentation is usually that we have a huge image and it has a lot of things in it, and we want to know that which for each of the pixel what kind of object it belongs to. So here's a visual example of these terminologies or tasks. Classification is if you have an image, we only need to tell that This is the image about cat. And if we want to do classification plus localization, then we need to tell that this is the image about cat. Then we also need to tell like where the cat was in this area. We usually use a bounding box to label where the cat is. And detection is usually in the image you have more objects than only one. They need to tell pretty much similar thing like in each local area, there's a cat and where the cat is. So it's kind of like a multi-object thing from classification plus localization. They need to also tell here's another area, then there's another object that is the dog. And then instance segmentation do it in more detail because for localization or detection, we only tell roughly where this thing is from a bounding box. But if it's for segmentation, then we usually need to do it very careful that we need to have a pixel level label, like these pixels belong to the dog and the rest belongs to other objects. Well, let's start with the concept one by one. Now we start with the object classification. So why object classification is different and difficult? It's needless to say that if you go to do a nowadays Google search or Bing search for images, then you know that there still is 2020. Then you will find the things you need, but you still find some misclassification. So this is a few interesting examples that if you want to search bagel, that you can get dog, or if you want to search dog, you can get bagel. Why is that happens? Because you know, how do you describe it's a bagel? You probably would describe the appearance in the image like it's brown. It looks like rain. Then you will find, of course, some of these things that follows the same description of a sleeping dog. And what kind of other things you can use to describe a bagel that actually is different from a dog? Well, of course you can say it's a food, but what makes this a definition for food? So why we're still asking this? Because you know, if you're doing a rule-based algorithm, if you don't tell your computer algorithms, make it very explicit, then the computer doesn't know because they will just follow this information you give them. Similar, one more idea. Here's a map, and map can also look very similar to docs, or docs can also be very similar to maps. And also croissant. And cookie. Finally, ice cream. Let's go for a little bit of more detail. What are those things we learned in low-level and mid-level vision that could make a image classification challenging? Let's start with one first thing that the orientation. So the object in the real world is always 3D, but the thing that we see is the 2D image. So it actually has been reprojected, and you have to tell the same object from different orientations. and illumination. So we learned all these things about lighting, how an object is collecting the light that reflected from the object surface, and arrived at camera. So the lighting condition can also make the appearance of a same image, same object very, very different. And occlusion. So not necessarily that in all the time that we see everything of an object. And scale change, but I think this is somehow easy to handle because we mentioned about scale in SIFT, the scale invariant feature transform. And also that a lot of the concept was quite vague. For example, this is concept chair. So how do we describe a chair that is useful for a object classification task? We can nominate a few. For example, a chair should have 4 legs. Then definitely in this collection, this is completely not true. And we can see that the chair has to have a bench. Then at least in this one, that's something useful. But if you also consider this is part of a chair, and then a chair has to have armrest, definitely not true for this one. And what else do you guys can think about trying to, it's sufficient to let the computer able to describe what chair makes the chair. And also, we see all these things that is visualized. We see color, we see light, we feel light. But actually, the computer is only processing these numbers. And also, one more thing, numbers of variables in the image is huge. For example, a HD image. And then if it's 3-channel, only RGB, then we know that they actually have 6 million input values. So to describe a tiger, in this particular image, our human was actually processing 6 million information, pixel values, without actually any conscious that we are actually doing that. Our human vision system can just do it immediately. But for a computer, for nowadays computer, then if you really want to have an algorithm that can do that, you need to process all this information. So the key idea is that they're at the beginning, because this is their introductory lecture, please really understand that we give all the basic concept, but object classification, machine learning in general is never going to be easy at current stage. Yeah, here's a quick summary of what we've been mentioned with examples. Please take some time to read it. Cool. Now let's start with the thing that how we tackle the problem about object detection. Here's the usual 3 steps, but I believe that probably you guys have already learned it from machine learning. that we usually sleep these things if we want to do classification, detection, then we do it in 3 steps. The first is to formulate your data. We put it in a database plus with the labels. So this is the standard step if you do machine learning. And then here that we usually call it image formation because we particularly deal with image for now. The second thing is feature extraction. Because if the data itself, the image is too huge and also you don't have useful information, you can't really directly do anything about it. So we usually process it and then we get things like features. So far, the only feature descriptor we give is the SIFT. We call it like SIFT descriptors, which is actually something that we can use to represent a local image patch on a particular scale. Those are kind of things we usually call them feature. And also that you can think like if you don't want to do anything, just the color value of an image then can also be considered as feature. Then the last thing is the thing that you guys do a lot in machine learning. Well, the final step, classification or decision making. So this is part we wouldn't need to talk too much in this course, but if we want to do image classification, we still talk about the first 2 steps a lot. Now let's start with the first step, feature presentation. Here are a few ways to represent a feature or an image. We can just use the pixels. Or we can try to somehow to describe an image. Why do we need that? Because we need useful information and also we need reasonable amount of information. Because like we said, if it's an HD image that has 6 million values, that is too much to do a classification without any further processing. And then we have local feature patches, which we already use it for quite a few tasks, including tracking and then image stitching. But it's also very important technology to use them for image representation or in general for classification. Well, we can just use the image value. For example, this is a synthetic human face. Then we can have a RGB value. We do it actually on a very short area. If you want to do image classification and then compare like if these 2 images, if you have already a sample image, a labeled image, for the one that we know this is a synthetic human, then we want to go to the database, give the new input, and try to tell whether the rest of them are human. But the pixel value that what we can do is that we have a pixel grid, we have a RGB value. If you really want to compare the similarity, then you can just do one by one compute the similarity by computing the value difference. Because in machine learning, that's the way to do is just to compare the Euclidean distance of data. But of course, that's too naive, and we know that therefore a real image doesn't work. That their similarity can be affected by, for example, if you do a local translation, then the pixel value on the grid is definitely different now. And if you're trying to do some occlusion, then quite a few values missing. And also you can do brightness adjustment, then the value is no longer stable either. So obviously translation, last week we already told you guys how to do that. And that actually makes if you just use pixel values for images, kind of very unreliable. So in the old times, just for your knowledge, but if you want to develop something really small, a really small and easy database and object classification, you probably still need this technology. But nowadays it's kind of like a little bit out of date. If you really need a very easy thing that can be useful, you can also consider to describe the image using its histogram. Because do you guys remember that in lecture 4 we talked about histogram equalization? Then for each image, then we can actually get its histogram. So that's actually a way to make an image represent an image in a database. Because each image supposedly will have a very different histogram. And also on the left side is an image with a few millions or nearly a million parameters or variants. But on the right side, you know that we only have now that there are 256 values. So if you want to consider the feature space or the data space, then you can have a much smaller data space and you can do much more to do the search and then analysis. But of course, a global histogram is definitely not reliable. So the first 3 images, if you want to convert it to histogram, you will know that these 3 will definitely got the same histogram. Similarly, for these 4 characters, if you just convert them to histogram, you will get probably very similar histogram. And then the local feature. We already had this set of images again and again for many times. But at the beginning we say that we just want to use the local features to stitch them together, do the image stitching. But you guys remember at the beginning when we're trying to do the image stitching, that we want to find the correspondence between them. So now that if we have a source image, and then if we can't find the correspondence in the target image, then what we can do, we can also do classification that we know that the target image and the source image, if there's a correspondence, they're supposed to be the same class. The local feature can also be used in image classification. And most importantly, because at the beginning we also mentioned about object detection. So as you can see that this thing also tells us where the desired object is. Then we can actually, for example, we want mountain, then we can put a bounding box here. So that actually local feature is also very useful to tell us the local locations. And then from now on, if we have enough sample and then in both computer vision and machine learning and later the deep learning course, you guys would definitely need to do this. And then at the beginning, we can tell the feature that its color, it's a local shift, it's a histogram, it's other things. But now that there's a naive way, you can just throw it into a convolutional neural network. But of course, the convolutional neural network has its own limitation, but at least for a very straightforward and easy and simple classification, it works way much better and is quite reliable now. We will have this in future lectures, but today we're still talking about some basic concept. So that if you don't have this, then a lot of this computer seeing anything is too black box, and you guys don't really know how to analyze. Well, local feature again, Harris Corner, you guys see it again and again. Shift, you guys see it a few times now. And then just letting you guys know it could be quite useful, especially not only the detector and also the descriptor. Because like we said that the image is too huge, then rather than store the image for further tasks, you actually only store the key point descriptors. So what do we desire? At the beginning, we mentioned quite a few challenges. about a feature, about an image that they make the classification difficult. In the list, the local feature can handle a few of them. For example, if your feature is scale invariant, then you can handle scale invariance. If your feature is rotation invariant, then your feature can handle that as well. The current safety description that doesn't really rotation invariant because we give this histogram in the locations. But if you're trying to align it a little bit, you find that the safety actually can be quite rotation invariant. Also lighting robust. I didn't mention it too much about SIF, but if you guys can try to test it a little bit, you will see that their safety feature was quite lighting robust. Why is that? Because it actually looks into the direction of local gradients. It doesn't really directly go for the absolute value, and then the gradients stays regardless of the lighting condition, unless it's totally bright and totally dark. If it's just a minor change of the lighting condition, the gradients doesn't change that much. And further, SIFT has converted the gradients to a statistic of the gradient orientations, so the change to according to lighting can be quite minimal. And also very similar to the thing like projection robust. So that's why the shifter plays a very important role before the convolution neural networks has been widely used. So here's a very quick summary, but it's very preliminary. If you guys will really do a hands-on, if you go to a company and you do a project about image classification, it's way much more complex than that. But for now, the basic concept is, the first step of an image classification is trying to present the images. And the way to present it is that you can just do it as a pixel value. You can do it globally, but we only shows like a histogram, or you can do it locally. Then we have already tell you guys about the Hawk. No, not Hawk. It's Canis Harris Corner, and also the SIFT. But you know that there will be so much other new descriptors that have to be proposed by a lot of researchers. Here's another way, the second way that there, other than just the SIFT feature, and we will give this concept a bag of words. That's another way to represent the image. And then for the exercise, you guys can actually need that. And also for the assignment next week, you guys will probably need that. So that's another way to actually represent the image. Um, I'm not very sure because information retrieval is in next period. But just assuming that I give a lot of examples about if you go to Google, then you actually try to find you can search and try to find a particular web page, and also you can go to the library and then you can search using a particular words. So what this system does is, because if it's library, it's a book, it's quite straightforward. The books or document is made of a lot of words. And if you're trying to search a document from a library, you just give your keywords, and then the search was actually scanning through each of the words and find whether there's a match of the words you want. So the concept is trying to store a document in a library. Then what you need to do is actually can just convert a document into a number of words. For example, I convert I to we like there's like a 1, 2, 3 at least, and a few I in the document, and then there's a few love in this document, and we just convert it like into a frequency statistic of each word for the later search or classification. So we want to really use this idea in image search as well. So here's the conversion. We just shovel it. We don't consider any document is still a document. Then we just think it's just a bag, and init is just a bunch of words. Then eventually we can have a statistic. It has 6 i's, 6 it, 5 I, 4 the, 3 to, etc. etc. So that's the way that we can convert a document into a bag of words and use it for text search. And now what we want to do is actually we want to apply exactly the same idea to image. And then we don't actually do a very naive thing. It's like there are like your 10 blue pixels. There are like your 10 like another blue pixels as 122. There's another like 20 blue pixels at 121. Because those things we already had it. What's the name of it? Yeah, the answer is image histogram. So we don't do it at the pixel level because otherwise we already showed you guys this is image histogram. We want to have things that is slightly meaningful because in backup words and a document, we know that each word still have some meaning and it's local. So we want to do the same thing. That we want to have an image patch, and the image patch is somehow representing something meaningful and it's local. So we do these things on image patch. And here's an example. What we do, for example, we want to find a patch. If that says like in this image, there's a eye, then that's the keyword that we can try to search this human. And similarly, if we have if there should be an eye in this image, another eye, there should be a nose in this image, and then there should be a mouth. If we don't think about the local information, then if we wanted just to do bag of words, then we can have all this information on left. If we want to search a database, then we want to find image of a human face. But of course, how do we find an eye? And actually, it has to do a further breakdown. Then we know that we need to find an eyelash, we need to find iris, we need to find eyebrow. So that the words can also be more detailed. Or a bag of visual words can usually just be considered in another vivid way. That if we want to find an image of human face, then you know that there's supposedly that the back should have the words like a mouth, a nose, an eye, chin. And then it can be just generalized to you know be quite general to any images, not necessarily to be an image of human. Then you just consider each of the local image patch supposedly should be a word. And then supposedly this image patch, we human can know that there supposedly should be a word about sky. And then there should be a word about water. There should be some other word about the boat. And then about the building. Then eventually this is kind of a set of word that can tell us this is supposed to be an image about a cityscape. And also this city has a river. It looks like a Netherlands, but I can't really tell. Is this Amsterdam? And similarly, as the thing we do with the words, then we just have a image that we just convert it into local patches. Then we actually try to group all those words. But like we said, when it's just a word, and group it is quite simple and easy. If it's the same words, we just put it together. But for images, a little bit different. For example, those patches are all skies, but they are slightly different. And how do we know that they're supposed to be grouped together? Yes, there's a technology called clustering. And then I think you guys have learned it in machine learning just last week. Yes, then we need to use it right away now if you need to do the back of words. Then you actually try to get a statistic about how many words, what is these visual words, and then what's the frequency of histogram. So these are the visual words we found. We usually call it a dictionary. And then we have the statistics, which is the histogram. So like we see that what's the difference between the histogram directly on an RGB image? Because yeah, if you try to do a local patch as small as 1 pixel, then you go back with the thing that we did on histogram operation as pixel level. But as you can see here, that this thing can actually be done at patch level. So the things is a few steps. Step 1 for image, we just try to convert it into patches. And then here's a step 2. For each patch, we still need to describe it. But usually you can just do it using the pixel value, but we know it's not reliable. Then you can do a little bit of sift visual feature, and you can try some other things. Then we can try to do a clustering. Then we find a dictionary. Then for each of the word in the dictionary, then we try to calculate how frequent that its frequency. Then we actually form, eventually the back and forth forms a dictionary along with its frequency. So another thing about it, why it's called dictionary, is usually that we show the example that they're only about one image. So you know that the same thing that if you have one image, that it not necessarily have every word, because for example, one image is about cat and the other image is about a dog. So that the cat word doesn't necessarily to appear in the dog image. And that's the same thing as document, that the first document is about one poem, and then the second document is about another poem. The word could be different. And that's why the dictionary is actually the collection of all the words in all the images in the database. So that's something that it hasn't been mentioned in the previous single image examples. So the dictionary is shared among all some image samples, and each image sample will have a histogram about the number of visual words that appeared in the dictionary. Step 1, patch sampling. Step 2, patch descriptor. Of course, we have a very limited number of time for our course, and we use Sift quite a lot because it's quite useful, quite reliable, quite popular. But it doesn't mean that you guys there's no other feature exists. So you know that in the final projects, if you guys like, and then you can do a little bit search yourself and also test all those other features. I'm pretty sure it's actually integrated in OpenCV. So if you guys using Python and you don't need to implement it yourselves, you can just use it. And then how to create a dictionary. Then you need to do the classic clustering. In machine learning, I'm not sure how many different type of clustering methods have you guys learned. We're just assuming that you guys have the basic concept what is clustering. That in a feature space, for example, each of the dictionary, a local image patch, can be converted into a feature vector. For example, if we're using Sift, we had a 128 dimensional feature. So this feature space was actually 128 dimensional, and each patch is actually a feature point in the feature space. Then you put all the patches in, and then the clustering is actually, if there's a lot of patch looks very similar or close by in the feature space, you just group them. I'm pretty sure k-means has been taught in machine learning. It will be used here, but it doesn't. But of course, if you guys want to really have more variation about the way to do clustering, I think there will be more in the machine learning textbook. And of course, there's some very basic concept in clustering. that it's needed everywhere. The intra-class distance of a class, it should be small, and also the inter-class distance should be as distance as possible. Now, here's the one more result of how to form the bag of words. Now we have an example of more than one images. It's actually 10 images now. All of them is about car. Then we actually, sample them into small patches, and then we do a clustering. Then we can actually form the dictionary. The dictionary is about there should be wheels, there should be windows. But another thing about, because the way we sample the image patch is that's based on its meaning, it's just a local slice of the patch, so that we can see that the image patch doesn't necessarily to be a specific local part that has a specific meaning, because after all, the computer only see pixel values. It's not our human brain that they don't really see meanings. And then this is eventually formed the dictionary for all the 10 images. And for each of the image, then you can actually have a later statistic. And here's the same thing that we can do it for human. But on the right side, this is actually the patches from a video. If you only look at single image, you don't see that many legs. Or it can also be from a number of image samples. Then eventually, once we got each cluster, then for each cluster, we count the number of samples belongs to that cluster. So we got dictionary, we got the histogram. Well, this is gonna be very useful later about bag of words, but still have some thing that is important and then limitations. For example, why the bag of words can somehow be unreliable is that it doesn't really give us any information about the spatial information. So if we're trying to shuffle a cat into words, for a human eye, we know that this is a really shuffled thing. It doesn't really have any structure in it. But if you use the bag of words algorithm, the computer doesn't care, because if you do the clustering on these patches and you calculate the histogram, you get exactly the same thing as the left image. So think about how we can actually solve it. One thing that is straightforward is actually you can just put the space information into your search. For each patch, you can tell that when you describe it in a dictionary, you can actually also provide a little bit about the distance information, the localized information. Let's have a break. Welcome back, everyone. Let's continue the lecture. So we still have quite a few concepts that is useful for the tasks, but we will go through it quickly because you guys should have already learned it from machine learning. We just show some easy examples how those things are interpreted in computer vision. Again, if we want to do image clustering, to do image classification, we have a recap that we want to have a database. We extract feature, and the last step is throw it into a feature space and also do a design classifier. Of course, we just show examples because you guys know pretty much how to do that in machine learning now. Again, we give a very, very simple example that we try to classify a set of images into two classes. One is apple, the other is orange. So we can have a feature vector for each of the image. Then can be many things like we said, global gradients, global histogram, local features such as shift, and then backup words. You can use any of them. But most importantly is those things convert a image into a feature. For example, for the histogram, the backup words use the histogram as the feature space. Then if you use shift, then you use a set of shift descriptor as a feature space. Here we show the example in 2D, then we can actually just use the shape and color. Then for shape, we can actually give a feature, for example, whether the shape of the object is very close to a circle. Then how to do shape analysis? Do you remember? Yes, we can need to extract the edges. Or once we have the edge, then we can try to do a little bit of geometric analysis whether it's sufficiently round as a circle. Then you can put a feature as a shape feature. And also another dimension, we can have a color feature. How to do color feature? Do you still remember things we learned in lecture 3? Yes, we can use CIE color value hues. But for example, here that we might have this array pointing here is more orange, pointing here is more red. Then we actually extract two features for each image, and then we form a two-dimensional feature space. In this space, we just put samples into that space. That's quite typical things we do in computer vision. Then here we use X for apple samples, and then we use O for orange samples. Then we form the feature space, and then there's one very straightforward way that we really want to just do a linear boundary. So anything belongs to below this boundary, then the classification is if you have any new sample, extract the feature, we throw it into the feature space. If it's below this boundary, then we believe it's apple, and if it's above it, then we believe it's orange. Here, I think in machine learning, you guys definitely have this idea that there, for the apple orange example I showed the first case that anything that can be, ideally separated, and also that the separation can be done by a linear separator. But also that there could be cases that your feature space is not really good, and then you might have something or more complex that you need to use a better classifier or decision boundary. For example, here is a nonlinear boundary. Or you could have a very confusing case. For example, here that the samples between two classes in your feature is non-separable. Will it happen? It happens all the time. If you go back to the slides of the course today, I showed you all the examples about this dogs and food, cat and food. So if you have a really weak feature, you can simply form a feature space with samples that is inseparable. And also, especially because in computer vision, in machine learning, that if you have an inseparable feature space, then we say that there's not too much that the machine learning can do. But in computer vision, there's a lot of things you can think. The first things first is just don't extract the feature that is not reliable. We give quite a few examples in global histogram. So for these examples, that was just a translation. And if you're trying to extract a global histogram and you're trying to form the feature space, then you got this inseparable feature space. So, but once the feature has been extracted, then there's not too much you can do now. But if you go back to the original data and you're trying to think about all these things in image, there's still a lot of things you can do. And those are the things now that most of the computer vision researchers will focusing on. Then what are the machine learning researchers focusing on? You have something that like this, or like slightly somehow separable or somehow not inseparable. the machine learning researcher might think about an algorithm, a learning algorithm, to somehow still trying to make these things separable. But of course, you know, the best thing if you're doing computer vision, the best thing is trying to get the good data and also trying to extract a reliable feature. Decision boundary. You guys definitely learned it in machine learning. So I would just quickly tell you guys that it's useful, very useful here. If you do image classification, for example, you can just use SVM support vector machine. I will skip the detail because I'm pretty sure these things has been covered. And then you guys has actually have a lot of theory and mathematics on how to do it. And also, it's supposed to be in a machine learning package when you're trying to do AIR assignments. The concept I have to emphasize is, precision and recall. Because this is some indicator that's very important for image classification. Because in machine learning, you guys can have quite a few other indicators. For example, ROC curve. But here we usually just use precision and recall. And also, why do we need that? Because we usually need that for evaluate how good our image search or image classification is. So actually, I use always like in a real physical lecture, I always give this example in front of everyone, do a real-time search. But unfortunately, this year we have a online pre-recording. So you guys can actually try to have a hands-on about this. Go to Google image search, search Apple, and also go to Bing image search and search Apple. So here's the result I did last year. And here's one result from one search engine, and here's another result from the other search engine. Can you guys give a guess which one is which? Um, in most of the lectures, existing lectures, that the popular guess is this one is Google, and this one is Bing. But the correct answer was that this one was actually from Google, and this one was from Bing. And also now that we have a question, which one is better? That depends on whether you want the food Apple or you want the electronic product Apple, branded as Apple. And then we can talk about like which one is better. So the thing that usually we use image classification, we use these indicators, the precision, transition, and recall. This is supposedly to be a recap of those things you guys got from machine learning. The thing is that we have a sample of images, then a few of them is actually Apple, and then a few of them are not Apple. And then if you try to do a classifier to classify them into Apple and non-Apple, then we have 4 possible outcomes. Is that this image is, for example, actually Apple, and then the classifier tells you it's Apple, then it's called true positive. And then we have another thing is that called false positive, means that those thing was actually not Apple, but your classifier tells them it's Apple. And similarly, we have another set, which is those things called false negative. That is, it was actually Apple images, but your classifier doesn't tell it is actually not Apple. And we have true negative, which are images which are not Apple, and your classifier tells them it's not Apple. Then we have this combination. The precision is among those things you said it's apple by your classifier said it's apple, how many of them are actually truly apples? And then here's another thing that is called record. It's among a set that actually has all the apples in it. How many of them actually has been found by your classifier? So here's the matrix about all those things. And we can have another indicator that is called accuracy. One more thing that usually the precision and record is not given as one number. Usually we give it as a curve. How to formulate this curve? Because you know that when we try to do decision boundary, for example in SVM, we can actually adjust the boundary. So once you adjust the boundary and the accuracy, the precision, and the recall, all those number changes. So that if you have the same feature space and try to adjust the decision boundary a little bit, you can actually form a precision and recall curve. Then you can have at a certain choice that the precision can be as good as 100%, but you can have a very, very low recall rate. And on the other hand, you can have a very, very high recall rate, but you can have a very low precision. And then actually, both of them are using very important applications. So I always give this question. When is the case that you want to adjust your classifier to have a very, very high precision, but you don't really care too much about the recall? Here's an open question, but I can give one example. For example, if you want to search, do image search, you just need an image of one thing you want. You just want to search and find an image about Apple, for example. Then what you need to do is that you don't need like in an ImageNet you have a million of images and maybe nearly a million of images exist online that's all about Apple. You don't need all of them. You just need all the images on the first page that is Apple, so you can just find the one you want. So that's the case that the precision is very important. That you want the images you found in the first page is pretty much all apples. You don't want anything else. But you don't really care that how many apples are there in the system. So that's the case that you want to adjust your algorithm, make sure the precision is high and the record is it doesn't matter about the record. How about the other case? It usually happens in security or health. For example, nowadays if you want to have a coronavirus check, then you really want everyone to be properly checked, even if there's some of them doesn't really have a coronavirus, but you don't want to miss them with the risk. So when you do the screening, you don't care too much about the precision, and then you want to just have anyone that is actually have a coronavirus infection want them to be found. Even it means like some of them doesn't really have it. You also have labeled them as potentially yes. And then similarly, that there for any other things in security, you do the same that you don't miss any potential risk. And why do we form a curve? Because of course that when you change the boundary adjustment, you will have this change. And it's another thing is that there's sometimes you want to find a proper balance. Well, here's the very last concept of multi-class classification, which belongs to object classification. Because until now we give all the examples about just for example apple, non-apple, which is two category. If you want to do a multi-class classification, it's quite straightforward. For each of the class, you just give one classifier. So if you need two class, then usually what you need to do is just yes and no as whether class A or class B binary. But if for three classes, then it usually is whether yes class 1, not class 1, class rectangle, not class rectangle with a decision boundary, or class, not class. So if you want to do multi-class classification, then all you need to do is decide one classifier for each class, but you still use the same feature space. I was told that you guys already learned this Boltzmann machine or the deep nets in general. Then that's the thing. If you want to apply it in a deep neural net, then the last layer, the full connected layer is the classifier. So that each of the node can be used here as like if you do food, and among these 5 categories, not necessarily food and animals, a lot of everything, then each of the node will be a classifier for a particular class. And also don't be surprised if you do image classification. If you want to do an image net with 10,000 clusters, then you can simply have the last layer have actually 10,000 class if you want. Cool. And in the last part of this class, we talk about another 2 applications. One is image retrieval, one is image segmentation, and we leave detection to next lecture. Image retrieval, like we said, we can do the visual querying. We can give an image of Paris. Then we want to search similar images online. But rather than we just do a keyword search, like we type in a word that is Paris or Eiffel Tower, we can just take in one photo, and then we use the photo feature, and then we're trying to extract the rest. And we have all these things about backup words. We talked about already that when you do a retrieval, you have a database, and then what do you do before you put the database online is to put the construct the vocabulary and dictionary, and then we convert all the images to the backup words histogram already and put it in the database. Then once there's a new image coming, then we trying to convert all the images into the feature descriptor, the backup words for the query image or the input image. Then once we get this feature, then we compare it into all the images in the dataset in that feature space, and then we'll rank it according to the similarity. There will be quite a few ways to compare similarity in a feature space. The easiest way is just to do the Euclidean distance, and also you can do the correlation. Once that they're in next semester, once you guys go to information retrieval course, then there will be a huge knowledge about how you can actually do it in a more complex and advanced way. But for now, we just consider the naive way, just the Euclidean distance or similarity or correlation. But it's quite simple, but that's still quite useful. And again, we have this concept again, that precision record for image retrieval. It's quite similar as detection, but the only thing is now the true positive is among the images that has been found out, and then those are actually the images you want. And then for retrieval, there's another thing which we call the average precision. That's just slightly different. It's actually an integration of your precision recall curve. Let's see how we do it. For example, the average precision for 3 documents is from this image is we go like let's assume that the first relevant document until now is number of relevant document, and they divided by the probability of finding a relative document. So we know that here that we go to the first image is the correct one. So the probability of finding a correct document within one number of relevant document is just 1 by 1. And then the second is, how about finding 2 relevant documents? Then we know that if we're trying to find 2, then the probability will be only 3 by 2, because the second one is the wrong one. If we need to actually find 2 correct one or relevant one, we need to go for 3 images. So the probability to find 2 relevant document is 2/3. Then how about trying to find 3? Then we know that we go for 4 images, we can find 3 relevant ones. Then the probability of finding that was 3/4. And then because we're discussing about 3 relevant documents, so that's the way to calculate it. But how about the average precision for 4 images? Well, at least for this query that we can't tell, then we need to go a little bit further. But that's the way to calculate the average precision. Here's the example of calculate up to 3 relevant documents. Here are more some example questions about what do you need to understand about trying to build an image retrieval system. But I'll give it an example as those things that you can probably encounter in the final exam. For example, like how big a image retrieval system can be. For example, let's calculate a little bit. Like if we have a query image of 100 and we have a dataset with 5,000 images, and then how big the feature space can be. And also that if you have 5 million images, how big the feature space can be. But usually in computer vision, we not talking too much about the computing power. But you know that in computer science, however, the computing power is always restricted and limited. For example, in Google, there are billions of images, and then you know that for each of the search you did with just simple input of one keyword, but it means like if you don't actually structure everything properly, and then you end up in the scanning through, for example, 1 billion of images for each query, then that's a huge amount of effort, and eventually it can go further into how much CO2 it emitted if you do a search, not brutal search. It costs a lot of things to the economy, but we don't actually need go too far there. But still, we need to keep in mind that handling things on image is always end up being a huge amount of data processing. So that's why we need all those things to make image smaller and easier to handle, but still reasonable and reliable. Well, last part, we talk about the task on image segmentation, because I think you guys already know that a little bit. Because when in color space, we give a very simple example. We can actually try to segment the image according to its hue. And also that they're in binary image analysis, it's black and white, and then we can just consider this already a segmentation into 2 categories. And then we actually use it for a CT image that we can actually somehow segment the organ. Now let's talk about it a little bit more. How about we segment this image? They will want to know that the pixel, that some of them belongs to water, some of them belong to grass. One of the important things is tiger here. The rest is some dirt. So that's the task we want. Or here's one more example. Then we also this kind of segmentation in most of times we call it a semantic segmentation. Is that we segment the pixel according to its meaning, because here the grass is something that we have a meaning. And then the war is something that it has a meaning, and then the caso is something has a meaning. So we usually call this thing semantic segmentation. Or better, we can also have some segmentation that doesn't have a meaning. That there, for example, here is the texture segmentation. Segmentation is the basic technology for many things. Here that we show that if we can segment the man out, then we can actually do image montage, similarly for the flower. But also we can use it to analyze the image. We want to know there's a man here, and we want to know there's his plants behind it, because eventually we can further infer this guy was probably in a botanic garden or in a park. So these things can be used for further analysis. And then his photo montage. Now that nowadays these things so easy and straightforward, it's just to do with Photoshop or any mobile app. But if it's 10 years ago, these things you really need to manually do it in Photoshop. That they're trying to, mark pixel carefully using your mouse and then trying to put it together. But if nowadays that you can pretty much do it automatically, that with a click, then the algorithm can tell you that this is supposed to be one cow, and the rest is just put them together. But however, there's always difficult cases. For example, here that should you actually do a segmentation the images into probably that they're according to color, or you're actually trying to detect things. Because what's the disadvantage if you're trying to segment things already? Then that if you segment this head out, then that this person and this person no longer belong to the same segmentation. You can't actually relate it again. But however, there's also cases that if you don't do segmentation properly, then the detection can also be quite complex. Because for example, for this easy images, that if I have many objects in it, then the thing is that maybe we can just segment it out first into different objects, then we recognize it one by one. But however, the previous image we gave, that's actually will cause some trouble. You will miss objects. And here's one more thing, that if you do the segmentation first, then eventually your recognition or classification algorithm can probably only find the rocks and also snow. But if you want to use it to find the horse, it's very difficult. Also, that for this particular image, if you want to do backup words, then you know that there's very unlikely your backup words algorithm can find the horse properly. There are always a lot of things you really need to solve and handle a real image. And all you need to do is think about all these things that we introduced in the lecture or on the textbook or any other open resource. What's the good point and what's the the worst point or the bad point? Then you're trying to think about it for your particular problem, which is the best tool you need to use. So here's a good example that if you can do a good segmentation, then the recognition can only be done in each region. If you can have the tiger here quite well segmented, then detecting the recognizing the tiger will be quite straightforward. But of course, there's always some exceptions. So for this course, we usually focus on these things that is really not that complex. Then we want to actually use out the low-level, mid-level visual cues. Those are the RGB values, grayscale values, or the local patches color, save the feature. And we want to use them to actually group the images into different categories. Then for each category, then eventually we try to do a recognition of what the object is. So this is usually called a bottom-up approach or a second-first approach. Here's a very straightforward thing because if you just use RGB value for each pixel, then you can actually already do segmentation. And if for some easy image, you know that it is actually somehow reliable, then you can, segment this out as the sky. This is going to be the ground, but there with some error if it's, the ground color can be quite similar as the building. Then definitely the trees. How to do it? Well, we just give one thing that there, we remember that this thing can be thrown into a feature space. Then we can actually do a clustering. And then in machine learning, there are many clustering methods. And in this course, we just very quickly go through k-means, which of course it has already been covered in machine learning, so we don't give too much detail. And then another thing is if you try to separate something out rather than put everything all together, you can also put two extra feature, which is the pixel location. Then that actually in some cases, if in a rainy day, the sky is quite grayish, then the ground is also very grayish. So if you don't put the location in it, then if you do the RGB only segmentation, then the sky and the ground can be put into the same category. You don't really want it, and then one thing to deal with that is put the location in. K-means is quite straightforward. Once we have the feature space, we have a lot of feature points there. All you need to do is try to group them together and try to actually minimize the interclass distance and then maximize the intraclass distance. But the one thing for k-means that we have to start with how many clusters we want. So that's one thing is the disadvantage of k-means clustering. That, for example, you need to specify this data has to be, clustered into 3 categories. Then we start randomly with a few key nodes. Then we're trying to actually just put all the other rest of the nodes into the closest category. So that's at the beginning. Here's the first iteration. But we know that because the random start of the nodes, it was not really a good idea. For example, we don't really want this part belong to a different cluster. Then what we do is actually we reassign the nodes to the center, so that when we try to calculate similarity using Euclidean distance, we can have a better calculation. So that's what we do. We actually got the mean value of each cluster. And we update the state. And we do the clustering again using the better center. We found that the gradually k-means will move this center to the better point of the cluster and then make the clustering more reliable. So here are a few questions about k-means. What kind of thing are we minimizing? I actually mentioned in previous slides. And also, this is a few analysis that could be important, that when you go to the exam, that you need to know what we are doing. And then the good thing is, I will leave this questions to machine learning in the computer vision exam, but I think in machine learning, you guys probably will be asked about these things. But here, why we mention this because we need this for image segmentation. A quick recap of step 1, 2, 3, 4 you want to do in computer vision. The only difference is here, the feature. What kind of feature you want? Color, texture, position, shift, or eventually deep learning. And then what kind of distance you want to use. Of course, as default, it can be Euclidean distance, where there are other better choices. And here's one more image that not only you can use it on a natural image, it is also very, very important for medical image analysis. And then if you can remember the segmentation we've done on a binary image analysis in lecture 4, then you will see that this segmentation is much clearer. And here's one more example. And then, is it a very good segmentation? Well, on the chili, I think it's quite good. But however, you can find if you only use color, and then, the little tomato is not there yet. And also that the cucumber has been categorized in 2 categories. But what if there's a problem there, each thing actually has been categorized into 2 categories? What can be done better? Well, use better feature. What else in k-means? K-means has to predetermine the number of clusters. Maybe you can adjust that. What else you can try? Well, the entire lecture we spent quite a long time to talk about backable words. Can you consider all this clustered image actually is one dictionary, and for each object you can actually construct a backup words for it? Yeah, that's something you can also try. But this is an open question. There's more things you guys can try. And here's only a few things that you want to consider, but it's definitely not the only thing you need to consider. It's definitely simple, and then it's kind of widely useful. But like I said, how many clusters do you need? And also the algorithm can be slow. And then if you have it also could be end up in a local minimum. When is that? Because we mentioned that the seed, the beginning of the algorithm starts randomly. And it could eventually end up in a local minimum. How to solve that? Well, a lot of technologies in machine learning, but actually in RANSAC, you see that you can actually randomize the thing a few times. Here's another thing that we can actually use SIFT and the k-means to build the visual dictionary for our backup words. Well, this is a lecture with tons of information, and it's gonna be the beginning of high-level vision. And then hope you enjoyed it. And then definitely for a lot of the concept, you guys need to go to the textbook, and then there will be assignments released. And then keep in mind our big project, the final project, will be the high-level vision. We will have 2 parts. One is applied in a traditional way, and the second part is applied in a very simple convolutional neural network. Good luck with everything and keep healthy. See you next time.